Okay, I wanted to go back to example 1 using the alternating series remainder theorem, which basically states that the error between your estimate and the actual sum is less than or equal to the first term where you stopped your sum. Okay, the first of the last of the sum. So we're going to do an example here. Illustrate part of the ideas. Okay, so you have this -1 to the, what was that, n plus 1, and n to the third. And they want us to find the value of the number of terms required to keep the error, which is s minus sn, okay, which we're calling the remainder. And we'll use an uppercase n here, not to confuse with. This theorem says that'll be less than or equal to the first neglected term in the sum. And in this problem, we're going to find how many terms is required to keep our remainder. We take this term, we want that less than 0.001. Okay, so we have to take our term, which is 1 over n. And we could work it either way. I could say n plus 1 to the third less than 0.001, which means 1,000 is less than n, well, that n plus 1 to the third power. So if you take the cube root here, you're going to have this, which means that the n plus 1 has to be greater than 10. So we would want our n plus 1 to be equal to 11. Okay, so use n plus 1 equal to 11. That means we need 10 terms. So in other words, the first 10 terms would be enough to keep the error in that sum less than the required 0.001. Okay, so back over here, use 10 terms to keep the error to be less than 0.001. Okay. Now to actually show this range of values here, we have to calculate S sub 10. You can do that on your calculator. I did it, and I got approximately, this would be S minus, I got about 0.90112. So here's our question. Do we have this? Well, we're saying that we're using this 1 over 11 to the third, because we're using our n plus 1 to be a third power. And this could be written as, whoops, hard to see that. Let's see. So this could be written as E. Okay, this could be written as S minus 0.90112. It's less than that 1 over 11 to the third. And it's greater than negative 1 over 11 to the third. So S is stuck between here. Our actual sum would be between 0.90112 plus 1 over 11 to the third. And 0.90112 minus 1 over 11 to the third. So that puts S between, let's see, I'm going to put that on the calculator here. Okay, so let's see, hard to see where my cursor is here. I'm at 0.09, oops, sorry. 0.90187 and greater than 0.900. Seven. Pretty close, though. As you can see, pretty tight range of values there. So that sum, by just taking 10 terms, you have a pretty accurate value for the sum, the entire sum. It's in between these two numbers. That's what the theorem guarantees.